Okay, let's dive into this. Welcome to today's explainer. Today, we're looking at how deep learning is literally revolutionizing complex mechanical design. We're talking about taking something as physically grueling and complicated as engineering a car's suspension system and handing the heavy lifting entirely over to an AI framework. It's an absolutely fascinating leap from traditional manufacturing straight into the future of engineering. Here's our roadmap for this explainer. First, we'll look at the perfect ride problem. Then the simulation cost bottleneck, the multi-fidelity AI solution, building the virtual suspensions, training the AI brain, and finally, designing the ultimate mechanism. Section 1. The perfect ride problem. Let's set up the core physical challenge that automotive engineers wrestle with every single day. So I want you to imagine driving down a road. Think about the massive difference in feel between a bumpy, rattling family sedan hitting a pothole and a smooth, high-speed sports car gliding over that exact same rough patch. Like, what dictates that experience? Well, it all comes down to one highly complex mechanism, the suspension system. Its whole job is to isolate the vehicle body from road irregularities while keeping the tires firmly planted on the asphalt. But as you can probably guess, designing the perfect one is a total nightmare of compromises. Now, one of the most common solutions you'll see out there is the McPherson strut. It's super widely used because it's genuinely brilliant at saving space and cutting down manufacturing costs. Basically, it integrates the spring and the shock absorber into a single strut. But, there's always a catch, right? Its lower lateral rigidity makes it far less suitable if you're trying to build a high-performance vehicle that really needs to corner at high speeds. Contrasting that simpler McPherson setup are the double wishbone designs. We've got a low mount on the left and a high mount on the right, which you'd typically see in racing cars. These bad boys offer superior handling and stability, mostly thanks to their two A-shaped control arms. But man, choosing between them and then figuring out the exact lengths and mounting points for all those arms, it's a massive headache. If you change just one angle to improve handling, you might totally ruin the ride comfort. It's just this endless, frustrating puzzle of trade-offs. Section 2. The simulation cost bottleneck. So why exactly is finding that perfect suspension geometry traditionally such a slow, agonizing task? Well, the traditional approach is basically a highly educated game of guess and check. Engineers pick a few discrete design samples, run them through computer simulations, and then try to refine them from there. But the nightmare here is that you're only looking at a tiny fraction of what's actually possible. You completely miss out on exploring the full potential of the continuous design space. And worst of all, as you try to get more accurate with your tests, the time and computational costs just absolutely skyrocket. It means engineers face a massive fidelity gap. Think of low-fidelity analysis like a rough sketch. It's fast, it's cheap, and it treats the car parts as rigid bodies. But it simply can't tell you if a part is going to bend or snap under stress. On the flip side, high-fidelity analysis is like a high-res 3D photograph. It calculates maximum stress using flexible bodies, like SAE 9255 steel. But it demands an incredible amount of computing power. You literally just can't afford to run it on thousands of different designs. Section 3. The multi-fidelity AI solution. Here is the breakthrough methodology that finally gets us the best of both simulation worlds. The answer to this problem is a multi-fidelity framework. Instead of choosing between fast but flawed or accurate but slow, researchers have figured out how to seamlessly integrate the two using deep learning. They basically use an AI surrogate model to bridge that huge gap between speed and accuracy. It's like teaching a computer to predict the high-res results by only looking at the rough sketches. Pretty mind-blowing, right? And this brilliantly illustrates the integrated design framework from a bird's-eye view. You can see how the system takes basic inputs on the left, like the type of mechanism, runs it through automated generation and dynamic analysis, trains the neural network right in the middle, and then spits out a fully optimized design on the far right. To keep us all anchored as we deconstruct this, here are the 5 distinct stages of this AI-driven pipeline. First, mechanism definition. Second, parametric design generation. Third, dynamic analysis automation. Fourth, the multi-fidelity surrogate model. And fifth, design optimization. Let's break down exactly how the framework pulls this off. Section 4, building the virtual suspensions. This is where we dive into the actual mechanics of how the AI starts creating and testing these designs virtually. So instead of human engineers painstakingly drawing individual CAD models, the system uses a clever statistical method called Latin hypercube sampling. It automatically generates hundreds of unique, evenly distributed 3D CAD models, like the McPherson on the left and the double wishbone on the right, in just a fraction of the time it would take a person. Once those virtual models are built, it's time to put them to the test. The dynamic analysis simulates the virtual car driving over a standard 10-centimeter high speed bump at speeds up to 30 kilometers per hour, and it meticulously measures 4 key things: maximum suspension travel, to see how well it absorbs the shock; maximum acceleration, to gauge passenger comfort; the first mode natural frequency, to really understand the vibration; and finally, the maximum von Mises stress, to ensure the steel won't yield and snap. Section 5. Training the AI brain. Now we get to see how the framework actually learns from all those simulated bump tests. The framework relies on a multi-layer perceptron neural network. What it does is take a massive amount of that fast, cheap, rigid body data and combines it with a carefully selected, super small sample. We're talking just 5% of the computationally heavy, flexible body stress data. Essentially, the AI learns the hidden mathematical relationships between the shape of the suspension and the physical stress it's going to endure, all without having to run the incredibly expensive simulation every single time. I really want to highlight this quote directly from the researchers. They state, "The multi-fidelity approach balances computational efficiency and prediction performance metrics, ensuring that the potential within the design space is significantly utilized." Okay, so what does that mean in plain English? It means it slashes simulation costs down to size while actually maximizing the discovery of brilliant mechanical designs that a human engineer might have entirely overlooked.
Section 6, Designing the Ultimate Mechanism. This brings us to the climax of the framework, showing the final, powerful output of the trained AI model. Because the AI has now fundamentally learned how these suspensions behave under stress, the workflow becomes incredibly simple for the actual automotive designer. Literally, all the designer has to do now is input the vehicle's sprung mass, which is just the weight of the car body. That's it. The AI instantly skips all those expensive, time-consuming simulations and immediately recommends the best mathematical parameters for the perfect suspension. The AI uses an algorithm called NSGA-2 to generate what are known as Pareto optimal solutions. So the crucial point is, this graph represents the absolute best compromises between ride comfort, handling, and durability. An engineer can look at this data spread and instantly pick the perfect suspension geometry for their specific goals, whether they're building a plush luxury sedan or a really aggressive track-ready sports car. To summarize the massive impact this AI framework brings to the table, it perfectly balances those conflicting performance objectives we talked about right at the start. If a target value shifts mid-design, no problem. The AI adapts instantly without needing weeks of new simulations. It practically eliminates those exponential simulation costs, and ultimately, it provides engineers with clear, fundamental design rules derived from deep data mining. Honestly, it entirely replaces the slow, traditional trial-and-error approach to industrial manufacturing. It's a total game changer. Which leaves us with this final thought. We're all so used to AI generating text, or writing code, or making images. But this explainer shows us something much more profound. AI is now successfully navigating complex, real-world physical constraints. It's balancing steel stresses, mass, and dynamic forces to design better, safer, and more comfortable machines for us. So the very next time you glide effortlessly over a bump in the road, ask yourself, will an AI engineer the mechanics of your next car? Thank you so much for joining me for this explainer, and keep exploring.